All right. So, good evening, students. So, today is the seventh lecture of the course series of this organometallic class titled as Transitional Metal Organometallic Chemistry by and the aid of organometallic transitional metal aided organometallic chemistry with the aid of their principles to applications. So today I have actually devised some basic problems on this transitional metal organometallic chemistry. This mainly involves some carbene complexes. Those are namely Fischer carbines and Schrock carbines. In the last slide also I have actually discussed about special class or type of carbene which has some intermediate properties between these Fischer and Schrock type of carbene complexes which act both with electrophiles and nucleophiles. So by going through each of the questions, the basics of this carbon chemistry will be cleared. So we shall start and with the first question. The first question is the carbon atom in Fischer type of carbon complexes is singlet and sp2 hybridized, or triplet and sp hybridized, singlet and sp hybridized, or triplet and sp2 hybridized. So many of you actually may have known the fact that this is actually singlet and sp2 hybridized. So we shall discuss a brief on this Fischer type of carbons. Then you can understand how they are acting as a singlet species and how they are sp2 hybridized, that are actually planar. So metal carbene complexes could be considered a Fischer carbene when the carbene is in their singlet state. Now, the delocalization of the lone pair from the substituent on this carbon atom. The carbenes can be classified or briefly termed as Cr2 species, where R is any kind of attached moiety. R can be hydrogen, R can be methoxy, R can be chloride or fluoride. So there can be different functional group can be attached to R. Now, the variety of carbenes can be described as Cr2 moiety. And here that I have shown there is a substituent is nothing but the R group. Now, presence of this lone pair of the substituent on the carbene carbon atom, you shall have to remind or remember the fact that in Fischer type of carbene, the carbon atom is connected to two such groups which are heteroatomic groups or which have lone pair of electrons. So sulfur, oxygen, nitrogen, these kind of atoms, when are bounded to this carbon atom, they are termed as the Fischer carbene. Now, because they have lone pair of electron and they are putting the electron density on the carbon vacant p orbital due to their plus R effect or the electron pushing inductive effect. So they are the carbene. So on account of that, the energy of the pz orbital or the LUMO of the orbital of the carbon actually gets increased. So instead of going to staying in the 1-1 pair, the all the electrons get paired up in cases of this Fischer carbene, because the energy of the other orbital is quite high, so electron cannot reside on that high energy orbital. So electrons remain paired up in the down orbital as the sp2 orbital. Thus the two electrons of the carbene are actually staying as an electron pair. That's why you can see in this molecular orbital diagram on the right hand side, this is the sp2 and this is the pz. All are having this 1-1 electron, and this is the sigma orbital from that. So after constructing the MOs, they are having this molecular orbital this, and these are actually having this slightly non-bonding character. This is actually non-bonding, but they have slightly anti-bonding character because it is closer to this pz, that is a non-anti-bonding. So here you can see this is a metal d sigma and d pi orbital. This is d sigma is directly bonded to the sp2 orbital of this carbene. You can see the free p or pz orbital of the carbene is this one. And as I have already said, any heteroatom that is actually having a lone pair of electron on its head is actually indication of the presence of Fischer carbene. Here you can see the OR, this is the alkoxy group, is actually attached to the carbon. So it is Fischer carbene because oxygen lone pair actually donates its lone pair of electron to the vacant pz perpendicular orbital to the carbene. That's why this PsP2 is actually doing a head-on bonding or add-on bonding to this d sigma of this singlet metal center, and they're actually bonded by the sigma bond. Here also you can see that bonding between carbene and the metal center involves a strong sigma donation from the sp2 orbital to an empty d orbital. This is the empty d orbital of the metal center. From this fulfilled sp2 sigma sp2 orbital, the sigma donation is happening. So from this, the electron is getting donated to the vacant d sigma on the metal surface, and then the d pi of the metal, that is actually field, is actually putting the back electron donation from the metal center to the vacant or empty pz orbital of the ligand. So that is actually having this back bonding. So here in the back bonding, what happens? Firstly, from the field sp2 orbital of the carbene ligand or Fischer carbene ligand, the metal d sigma is accepting the electron, and then from the fulfilled d pi orbital on the metal center, a weak pi back donation is happening to the weak pi donation on the metal center is happening to the empty pz orbital of the carbene. Here, why it is weak? Because the presence of this electron rich oxygen atoms, oxygen is actually putting the or increasing the electron density on the carbon center. That's why the metal is having less electron density on site on itself. That's why the electron donation from the metal to the carbon is actually weak. The sigma bond is actually stronger, the pi bond is actually weaker. The carbene, that's why the carbene carbon is electrophilic in nature. You can see I have actually stated, that's why the carbene carbon here is electrophilic in nature, and that is actually it is having a positive charge. That's why the heteroatoms are there to stabilize the positive charge on the carbon. So carbon is actually here is behaving as a carbocation. The carbocationic nature of the carbene is actually indication of the presence of Fischer carbene. And the metal atom is obviously will be nucleophilic in nature. That's why the ligands attached to the metal center here will be pi acidic ligand that will be dragging the electron density from the metal center. So CO, NO2, cyano, these are or phosphine to some sort, are actually the efficient ligands for stabilizing the metal in their lower oxidation state. So whenever you will see the CO kind of ligands are attached to the metal center, that is dragging the electron density from the metal center, and when you will see the electron donating heteroatomic substituents on the carbon center, it will be indication of presence of the Fischer carbene molecules. So coming to the second question, this question is regarding the other type of carbene, that is the Schrock type of carbene complexes. This actually the four options are singlet and sp2 hybridized, singlet and sp hybridized, triplet and sp2 hybridized, or triplet and sp hybridized. So the correct option here can be both C and D, triplet and sp2 hybridized. Still I have stated it is actually triplet and sp2 hybridized, but I will state how this can be modulated by the aid of this molecular orbital or picture. So here I have actually stated these two orbital question. The triplet carbenes are actually reverse in their activity or their properties in contrast to the Fischer type of carbenes. Here you can see these are actually the second option, that the isotope is just triplet carbene, that is the Fischer type of carbene, and this is the singlet carbene, that is the this is triplet carbene, that is the Schrock type of carbene, and this is the right hand side is the singlet carbene, that is the Fischer type of carbene. Here the triplet carbene, in the singlet carbene I have already stated, this is the vacant p orbital, pz orbital, and this is the sp2 hybridized carbon, and this is the sp2 orbital that is fulfilled. And by the aid of this sp2 orbital, the metal d sigma is actually getting bonded. But in case of this triplet carbene, this carbon may be sp2 hybridized as well as sp2 sp hybridized. Both can be possible. In some cases, this can be an intermediate sp 1.5 kind of sp1 or sp 1.5 kind of hybridization or mixed hybridization in case of the triplet carbene. Here the p orbital is actually having this one electron, and this sp2 orbital is having this another electron, and this p orbital is not actually entirely vacant, nor the sp2 orbital is entirely fulfilled. Here on the right hand side you will see that is a triplet carbene. Here you can see this is a linear geometry where this is 2py and this is 2py, this is 2px, and this 2py and 2px, all these orbitals actually having one kind of electron. But in the right hand side you can see this left hand side is the linear geometry. Here you can see the substituents are actually are opposite or trans to each other. That's why it is the linear geometry. So you know the linear geometries are actually sp hybridized. But on the right hand side, you can see there is the two substituents are actually cis to one another. That's why these are actually bent. Why what happens? Because this sigma, there is the sp2 orbital, and these 2p pi, there is the orbital, are actually having one electron. That's why the two or the substituents are actually here are bent. That's why this is the sp2 kind of geometry. So on basis of that, the highly reactive carbene species can be classified into two main aspects. Firstly, the singlet carbene and triplet carbene. Singlets are actually provided by Fischer type of carbene complexes, and triplets are actually the Schrock type of carbene complexes. Triplet carbene all are actually sp2 or sp, both can hybridizes are actually possible. In majority of the cases, this is sp2 hybridized, but it can be sp hybridized also, based on the orientation of the substituent groups. And because of on depending upon that, it will depend when or why this 2px or 2py will contain these two electrons, or this 2p pi and sigma will contain these two electrons. So next question here is actually a very popular question. It is very important also in the context of formation of these Fischer carbene complexes. Firstly, the question is this tungsten hexacarbonyl, that is WCO whole 6, when it is reacted with this alkyl lithium in ethereal solvents at a very low temperature, a cryogenic temperature, that is minus 70 degrees Celsius, and then the corresponding compound is treated with this trimethoxy tetrafluorobromoate complex, that is the Me3OBF4. So what is the product? So let's come to the point how this is actually happening. So firstly, when this tungsten hexacarbonyl is treated with this alkyl lithium, this RLi ether sorbate, what happens? Here you can see that is the all these are actually coordinated CO. So all COs are actually coordinated to the metal center. That's why the tungsten is in low oxidation state, that is actually zero, and that's why all these pi acidic ligands are actually capable of dragging the high electron density on the tungsten metal towards itself. That's why this compound is stable. So pi acidic ligands are actually very much important in stabilizing the lower oxidation state of this transition metal. So what happens then? So that is coordinated CO is actually having a larger positive charge than the free CO or the uncoordinated CO. You can see that this CO is actually termed as C minus O plus, having a triple bond between this carbon and the oxygen. But here what happens when this metal is actually bounded to this CO, what happens? This carbon is having actually this more positive charge because of the effect of the metal. Metals are actually electropositive in nature. That's why the larger positive charge is now larger positive charge on the carbon is actually happening, because the oxygen is actually having this electronegativity, so the carbon atom will be having this more positive charge. So the more positive charge is occurring on the carbon. That's why it is actually being more electrophilic in nature. So the nucleophilic attack of the RLi on the CO is more favorable. That's why this R is actually attacking on one of the coordinated CO, and the O minus will then grab this lithium while form this acyl salt, WCO whole 5 RCOOLi. So this acyl salt will be prepared. Now you can see that is the acyl salt is actually treated with this trimethoxy this tetrafluorobromoate. This Me3OBF4 is an important reagent in case I should say, because it is an important methylating agent. It is a very strong methylating agent, because you can see this OMe2 is actually neutral, but whenever OMe2 is then actually is tri-coordinated or actually having this another Me, it is actually having Me3O plus, and for this small oxygen atom to actually take up these all three methyl groups around itself actually quite difficult. So it will be very prone in liberating one of the methyl groups. That's why it is a very strong methylating agent. So this methyl group will actually be attacked by this O minus, and this methyl group actually will having this O minus, and Me2O will be liberated as a living group. That is dimethyl ether, which is very stable molecule and volatile also. So this OMe will be formed, and the lithium plus will take up this BF4 minus and will be liberated as lithium BF4 salt. So Now this RCO will be, this acyl moiety will then become as this RCOCH3 will be bonded to the tungsten. Here you can see in the last example, I have already stated that whenever you, how would you recognize the Fischer carbene? In Fischer carbene, the carbene carbon atom will be attached to the heteroatom containing groups. So here you can see this is a methoxy, and it is actually heteroatom with a lone pair of electrons on itself. So it will be stabilizing this carbocationic behavior of the carbon, and this tungsten is actually coordinated to all these 5 CO. I have already stated that these pi acidic ligands, which are capable of dragging the electron density from the metal like CO, are actually recognizable for the presence of Fischer carbene. So this molecule is actually a Fischer carbene, which was synthesized by Fischer, the scientist itself, in 1964, and that's why from this neutral tungsten hexacarbonyl moiety, where they are actually producing this Fischer carbene containing this WC double bond. So coming to the fourth question, this is the prediction of the reaction when this rhenium complex having this Cp minus ligand and also this acyl moiety and this NO plus in the form, and this neutral PPH3 moiety. So this compound is treated with this CF3SO3H. It is the strongest organic acid, that is the trifluoromethane sulfonic acid. So what is the product when this rhenium Cp minus complex is treated with this strong trifluoromethane sulfonic acid? So this is actually another class of reaction where the Fischer carbenes are produced. These are actually first produced by the scientist Gladys in 1983, when they have shown this presence of this such strong organic Bronsted acids will be actually useful in producing Fischer carbenes from these acyl coordinated metal systems. So here you can actually on your own count the balanced electron count of this complex, of this rhenium complex. What happens in first case, this oxygen is actually having this negative this lone pair of electrons, and since this trifluoromethane sulfonic acid is a very strong acid, because trifluoromethane sulfonate moiety is a very strong conjugate, very strong and stabilized conjugate group, because of the presence of these 3 fluorine atoms, which are actually electron withdrawing in nature. So the SO3 minus group will be highly stabilized. So this is having their pK in the range 1 to 2. So this is a very strong organic acid. Now this oxygen of this acyl moiety that is bound to the rhenium center is actually hard in nature, because oxygen itself is a hard center, and this trifluoromethane sulfonic proton is also hard. So this oxygen will be bound to this H, and this double bond will be shifted between this rhenium carbon bond, and this carbene carbon kind of system will be formed, and this oxygen will be treated as then an OH or hydroxyl moiety. So this is again a present in it is actually again is recognizable as a Fischer carbene, because you can see this rhenium is actually connected to this Cp minus is not a pi acidic ligand. You can say why I have already stated the Fischer carbenes are actually those which are having electron withdrawing substituent electron withdrawing ligands or ancillary ligands. But here you can see this NO is actually present. NO is a very strong electron withdrawal, or is a pi acidic ligand, which is even stronger than COs. And PPH3 also, by the help of this PC sigma star low lying orbital, it can also drag the extra electron density from the rhenium center. The electron density of the rhenium center is also increased by the presence of the strong pi donor ability of the Cp minus, that is a cyclopentadienyl ligand. But presence of this NO and PPH3 is actually helping rhenium to stabilize in this low oxidation state or the high electron density on itself. And also this carbon is actually bound to this methyl and the OH moiety. This OH is actually a heteroatom containing group which is having a lone pair of electrons on it. And so this is the classical Fischer type of carbene that is synthesized from this rhenium NO acyl complex by just treating it with the trifluoromethane sulfonic acid. So here actually the same explanation arrives that the C atom in the coordinated CO is also having this larger positive charge than the free CO. So any kind of nucleophilic attack of this oxygen is actually favorable in case of this metal coordinated acyl moiety. In the last example also you saw in the Fischer type of carbene, when tungsten was there, the CO is actually getting attacked by this R alide. This is the alkyl lithium. The R minus is actually attacking on this carbon. Here also the oxygen actually plays the crucial role, because it is having a more negative charge on it, because the carbon is more electropositive. So oxygen is actually having more electron density on it. That's why any kind of alkylation or protonation or then neutral acyl complexes is feasible in this case. Had not this acyl group will be connected to the rhenium center, the reaction would not be feasible at all. So coming to the next question, this is a very popular question where a Schrock type of carbene compound will be formed. Here, what happens in the first, the reaction is Cp2Ta Me2. This is the compound is having this positive charge on it. That is Cp2. The tungsten is when it is treated with sodium methoxide in methanol. What is the product? So in this case, what happens in first case, sodium methoxide is a very strong base in nature. It is also a very strong nucleophile, but it is a very strong base also. And whenever it is actually treated in methanol, we have to understand whenever sodium methoxide in methanol solvent is there, it will be more of be behaving as a base, not as a nucleophile. And here the actually the methyl groups which are actually bound to this tantalum metal is actually having this acidic hydrogen. These acidic hydrogens will be taken up this sodium methoxide, the strong base. It will be liberated as methanol, and this CH bond will be then come to this TAC bond, and the sigma bond will then be behaving as a pi bond. Then the compound Cp2T double bond CH2CH3 will be formed. So this is a special kind of compound. This is a Schrock carbene, not a Fischer type of carbene. So two actually characteristics are there that will help you in understand how or why these compounds are actually Schrock type of carbene. Firstly, let's come to the metal. The Cp minus ligand, that is the cyclopentadienyl ligands, are actually electron pushing sigma or pi donation ligand, and they're not actually any kind of pi acidic properties are there. So that's why these are actually Schrock type of properties. And here the carbon center is not having any kind of heteroatom containing groups like SMe or OMe or OH. They're actually hydrogens are neutral substituents. That's why this Cp2Ta double bond CH2 methyl containing compound is a Schrock type of carbene, not a Fischer type of carbene. This carbon, the methyl of this tantalum is actually adjacent to it. That's why it is alpha. So here you can classify this reaction as an alpha deprotonation of the metal alkyl group. So the next question is coming as the same rhenium complex. Instead of this acyl moiety, this methyl moiety is there. Rhenium NO PPH3 Cp minus, and this methyl is there. So what happens when this compound is treated with this PH3C plus PF6 minus? This is a trityl cation or triphenyl methyl cation, and the corresponding anion is PF6 minus at a very low temperature in DCM solvent. So this reaction is actually quite important for the formation of this kind of a carbene, which is actually intermediate in between Fischer and Schrock type of carbene complexes. Though I will be stating this guy is a more Schrock type of behavior than Fischer. So here you can see this is a triphenyl carbenium or trityl or trityllium hexafluorophosphate. It is a popular organic salt. It is a very important salt as commercially available as a brown powder. This PH3C plus PF6 minus compound. That is actually, it actually readily hydrolyzes to triphenyl methanol. The molecule, the moisture, whenever it is coming to a contact of moisture, from the moisture it takes up this OH, and it will be behaving as PH3COH. It is triphenyl methanol. It is actually used as a very much hydride abstractor reagent in the organic synthesis. It is actually very much useful in the synthesis of whenever a metal alkyl complexes are there and metal alkyl or metal alkynyl complexes are there. This PH3C plus F6, you should have a note on this reagent, or you can also Google about it, how they are functioning. They're actually kind of hydride abstractor molecules. These are actually again established by the scientist Gladys in 1983. So when they have treated this rhenium bound methyl complex, when the other ligands are PPH3 NO and CP minus, when what happens, this PH3 C plus, on account of its high hydride abstractor ability, it actually abstracts this hydride. You can see that all, I mean, there are many hydrogen atoms in this molecule also in the form of Cp minus, but the Cp minus are actually bound to strong CsP2 carbon atoms. So the CsP2 carbon hydrogen bonds are actually even stronger than the CsP3 hydrogen bonds. That's why they are actually prone to abstract these methyl protons rather than the CpH protons. So one of the methyl protons is abstracted, and the double bond is occurring between this rhenium and this carbon, resulting in a carbene complex, and PH3CH is the other compound, and the PF6 minus is actually going to the metal center to become as a carbo or to behave as the counter anion. So what happens here in this case, this PHCC plus, I have already told, is a potential reagent known to abstract hydride from all kind of metal alkyl or metal alkynyl complexes. So here the alpha deprotonation is also happening, just like the previous example. This methyl group is alpha to this rhenium center, and this PHCC plus is a very stable non-planar carbocation, is abstracting this hydride from this methyl group, and the rhenium carbon double bond is getting produced on account of this the intermediacy between the Fischer and the Schrock type of carbene. Why it is it is called as intermediate? Because you can see the carbon center is not actually having any substituent which is having a heteroatom or the electron donating ability. The hydrogens are actually neutral, so it is a characteristic of the Schrock or triplet type of carbene complexes. But in the case of the metal is actually bearing these two pi acidic ligands, which are actually capable of dragging the extra electron density from the metal center, NO and PPH3. NO by the help of this low lying pi orbital, and this L PPH3 by the aid of this PC sigma star orbital. Here the metal center is actually indicating towards the formation of this Fischer type of carbene, but in the carbon, its organic part is actually pointing towards the Schrock type of carbene. So that's why it is called as an intermediacy between this Fischer and the Schrock type of carbene compounds. The next question is regarding this formation of again this carbene type of compounds from this tricyclophenyl molecule when the gem dichloro moiety is present. So here you can see all the carbons are actually substituted and no hydrogen is present in this molecule, where this gem dichloro compound is actually present. Gem dichloro alkyl compounds are not that much stable. When it is treated with Na2CrCO5, again it is a metal carbonylate, and I have already stated that metal carbonylates are actually behaving as super nucleophiles, so it will be actually having very much poor electron density, and because of the presence of this this pi acidic ligands, the negative charge on the metal center is stabilized. But these are actually highly reactive in nature, and they will be attacking on the carbon center, which are actually having this carbocationic kind of behavior. So what happens in this case when this Na2CrCO5 in THF at a low temperature is treated with this gem dichloro cyclobutadiene. Okay, so this Na2CrCO5 when treated is having a di-negative charge because there are two sodium atoms and chromium is having a di-negative charge on it. And here you can see this is a gem dichloro molecule which are having two CCl bonds, both of which are actually labile in nature. So what happens? Firstly, the one more negative charge is actually attacking on this carbon center, which is having this. You can say this is actually a quaternary carbon, and SN2 reaction between a quaternary carbon and a nucleophile is not that much stable. So why it is happening as such? Here you can see the effect or the quality of the electrophile and the quality of the nucleophile actually plays the crucial or pivotal role, because the CCl molecule, that is a gem dichloro molecule, and gem dichloro molecules are actually very much unstable in nature. Also, This is a cyclopropenyl kind of system. Here you can see the phenyl groups are there, and this is a double bond, and this is having 3 carbon atoms, this ring. So this is a cyclopropenyl kind of system, and you know that a cyclopropenyl carbocations are actually highly stable in nature because of the aromatic character of this ring, because the ring is having this 2 pi electron. By the help of Huckel's rule, you know that is the 4n plus 2 kind of systems are aromatic in nature, and they're actually very much stable. So whether the reaction is proceeding by carbocationic behavior, that is the SN1 mechanism, or whether the reaction is happening by the SN2 mechanism, in both the cases the reactions are quite feasible. Because if we take up this reaction as an SN2 reaction, the strength of this nucleophile, that is CrCO5 2 minus, is high, very high, so high that it can actually break any CCl bond despite it is having this 4 substituents. And also, if we take up this as an SN1 reaction, this breakage of CCl bond is quite facile in nature, because this carbocation generated will be highly stable, because it's a cyclopropenyl carbocation, which is also stabilized by the plus R group of this phenyl ancillary substituents. So in both the cases, whether it is SN1 or SN2, firstly this one of the mononegative charge will attack on this carbon, and this one CCl bond will remain, and this chromium carbon bond will form. So this is actually a very classical example, when this scientist Ofele has actually denoted how this in 1968 how you can prepare this chromium kind of carbene complexes. So the next step is actually quite easy. In the first step, one molecule of NaCl will be liberated, this Na plus and the Cl minus from this olefinic moiety. In the second case, we are having this one of the Cl groups is here, and another negative charge will be there with the Na plus. So again a nucleophilic attack will be there, and this NaCl will be liberated. So 2 moles of NaCl will be liberated, and again a double bond will be formed between this chromium and the carbon. So that's why this Fischer type of carbene compound will be formed. How it is a Fischer type of carbene, we will again take up this example, because the CO molecules are there, and COs are all pi acidic ligands. That's why it is a Fischer type of carbene, the metal center. The low oxidation state is stabilized by these pi acidic properties. And also, though there is no heteroatom here, I've already stated the heteroatom containing groups when attached to carbon are actually behaving a Fischer type of carbene. But in this case, the phenyl group, on account of this extended pi conjugation or pi network, they're actually capable of donating the extra electron density to the carbon center. That's how the carbocationic behavior of this cyclopropenyl moiety will be stabilized. So that's why this CrCO whole 5 cyclopentadienyl diphenyl substituted moiety is a Fischer type of carbene complex. The next question is regarding this special compound. There is the PPH3 whole 3 osmium NOCl. This is an osmium 0 kind of system. This is a NO plus and this Cl minus actually counter anioning as one another when it is treated with this diazomethane at a low temperature. What is the product? So diazomethane is actually a source of free carbene, and is a very strong methylating agent also. Diazomethane is actually extremely air and moisture sensitive, and it is actually, when it is taken in solution, it is behaving like a yellow liquid. And this diazomethane handling is actually very much should be handled with caution. This PPH3 whole 3 OSCl is a special class of compound, because this osmium compound can generate a special kind of carbene that is actually intermediate between the Fischer and the Schrock type of carbene. So in the later examples, we will discuss why it is so. Firstly, let's discuss about diazomethane. Diazomethane actually stays in these resonating structures, CH2 minus N2 plus. In the first structure, you can see this is the carbon is negatively charged, and this N2 is having this positively charged. And in the next resonating structure, this negative charge will be down dropped off between this carbon and nitrogen, and this bound nitrogen will take up the electron. So it will be again having this tetra-coordinated nitrogen with the N minus and N plus to one another. Here you can see, because of the low molecular weight and the addition or the adjustment of this N2 plus group, that is a very good leaving group, because N2 plus will be liberated as a very stable neutral moiety N2. That's why diazomethanes are actually very strong methylating agent, because any nucleophile will be attacking on this carbon which is actually electron deficient in nature. You know, all the carbene compound are actually having these 6 valence electrons. That's why the octet is not fulfilled. That's why they are very much electrophilic in nature. So any nucleophile will be very much prone and will be dragged towards this carbene, and this CH2 will be attacked, and with the concomitant release of this nitrogen, that is a neutral moiety. That's why this CH2N2 is very much explosive and moisture and air sensitive, also handled and should be handled with utmost care. So what happens when this PPH3 osmium ClNO compound is treated with CH2? Firstly, one of the neutral ligand will be dissociated, that is PPH3, and this osmium Cl moiety will be there, and this with the NO and Cl will be remaining, but this will be attacked by this CH2. This CH2 will be attacked, and with the concomitant release of this dinitrogen molecule. So osmium will be having a double bond with the carbene of the carbene center of this CH2. So the osmium carbene carbon compound will be formed. On the first glance, you will see that this is actually a Schrock type of carbene, because the carbon atom is not having any heteroatom kind of substituents. But whenever you will take up a look on this metal center, it is having this pi acidic, extremely pi acidic, this NO, because in the spectrochemical series of the ligands, NO is residing on the top. And these PPH3 are also actually capable of dragging the electron density from the metal center with the help of their low-lying PC sigma star. This chloride will be pushing the electron density on the osmium, but due to the presence of this large 3D orbital, they will be again capable of dragging the electron density from the osmium center. So the metal center here also is indicating towards presence of this Fischer carbene, but the carbon is actually going towards or presence of this Schrock type of carbene complexes. These are actually again vessel scientist Roper actually have shown in 1983 how this OSCl-NOPPH3 whole 3 molecule is actually producing, one account of treating with diazomethane. It is producing this special type of intermediate carbene which is having a property between Fischer type of carbene and Schrock type of carbene. So this carbene complex is actually extremely important because it is having both Schrock and the Fischer type of properties of the carbene. The next question is regarding the CO staging frequencies in IR or Raman. So the 3 compounds are actually here given, which are namely firstly the chromium hexacarbonyl. The second option is the methoxy methyl C double bond CrCO whole 5. It is the Fischer type of carbene, classical Fischer type of carbene. And the last compound is an NaC type of carbene, NaC of this NaC is bound to this CrCO whole 5. So in all the cases, the CO staging frequencies, you have to arrange them in the ascending order. So in this case, firstly, one by one we will see how we will account for the CO staging frequencies. Here you can see the ancillary ligands are present in these B and C compounds. In A, it is completely neutral. No ligand is actually present to this or bound to this chromium center. In the first case, the chromium is actually bound to this carbon, and carbon is attached to this heteroatom containing this methyl, and this is the methoxy. Both are actually capable of donating the electrons. Methyl through the help of hyperconjugation, and methoxy with the help of this plus R donation property of the lone pair on the oxygen atom. Here the beta is there, or in this case this is an NaC or N heterocyclic carbene compound. This NaC is also capable of donating this electron through this carbon by the vacant p orbital on this carbene carbon. It is also a Fischer type of carbene compound. These two are Fischer, and this is a neutral metal carbonyl system. So the beta is the ligand, the sigma donation property, and the more is the electron density will be happening on the carbonyl moiety. Because the more there will be electron density on the more will be the donation power of this ancillary ligand, the more the metal will be throwing the extra electron density on it to the pi acidic CO. The CO is having this low lying pi star LUMO, and the more the metal will be having this electron density, the more it will throw the extra electron to the pi acidic ligand CO. So then the CO is having this extra electron on this pi star LUMO, that the bond order will be dropped, because the anti-bonding electron density will be increased. That's why when the bond order will be dropped, the bond strength will also decrease. That's why the stretching frequency in either IR or Raman will also decrease. So here we have actually come to the conclusion that the better will be the sigma donation property of the ancillary ligand, the more will be the electron density. The more will be the electron density on the metal center. So the metal center will be throwing the extra electron on the pi star LUMO of the carbonyl compound. This carbonyl will the pi star LUMO, when it will be having the extra electron, so the bond order will drop down, and also the stretching frequency will be lowered. So in case I have actually tabled up the data for you. In the first case, you see when there is no ancillary ligand, the stretching frequency in Raman is 2108 centimeter inverse. In case of this, when the methoxy group is there and the methyl groups is there, both are actually pushing the electron on the chromium metal, so the extra electron density is shifted to the carbonyl moiety. So the CO that is trans to the carbene carbon is having this IR stretching or the Raman stretching at 1953 centimeter inverse. So at a glance, what happens? This is, in this case, you can see that is the 55 centimeter inverse drop down in the mode. This is a, you cannot a 55, because you can see this is 5, this is 590. It's a 105 or 145 centimeter inverse decrement in the new CO in the Raman spectroscopy, because the methoxy and the methyl all are actually pushing the electron density. That's why the lowering of the stretching frequency in the CO is observed. But here you can see again the new CO that is trans to the carbene, that is the N heterocyclic carbene, is again dropped down by the amount of 36 centimeter inverse. So we have actually come to the conclusion that in heterocyclic carbene compounds are actually more electron donating than the corresponding Fischer type of carbene complexes. Why it is so? Here you can see only one oxygen atom is putting the electron density, and you know the hyperconjugation from methyl is not that much prominent in nature, not that much electron pushing. But here you can see both the nitrogen atoms are actually bound to the carbon, and because nitrogen atom is also more electropositive in nature or less electronegative in nature than the oxygen, so the electron donation property of the nitrogen is more. That's why, since they are both nitrogen atoms are there, so the electron donation property of the NaC is actually far better than the sigma donation property from this Fischer type of carbene. That's why in this case the new CO trans to the carbene is actually having stretching frequency even lower than this Fischer carbene, that is 1927 centimeter inverse. So this is how the order is justified, that is CrCO whole 6 is having the most, then it is the Fischer carbene, and then it is the this NaC. So in the ascending order, the answer will be NaC, this compound C, less than this Fischer compound, and this is again less than the chromium hexacarbonyl. So this is a question. This is a next question. When this metal CO whole 5 moiety that is actually bound to this lactone kind of system, when it is treated with CAN, that is the ferric ammonium nitrate. Ferric ammonium nitrate is a very popular reagent which is actually treated as an oxidant in nature. And the next compound is actually again MCO whole 5, where M is chromium, molybdenum, and tungsten. Here I have already told you guys, and by actually going through all the slides, you have already known that in this case, when the metal is actually connected to the CO and this pi acidic moiety, Fischer kind of compound, Fischer type of carbene complexes, and also they are having heteroatom kind of substituents, and also they are actually having these hyperconjugative CH2 moieties. So although both of them are actually Fischer type of carbene complexes. So these two Fischer type of carbenes, when first one is treated with CAN and the second one is treated with DMS, which is dimethyl sulfoxide. What are the products? In the first stage, the product is this one, and in the second stage, the product is this one. In the both the cases, you can see the reaction is same. The metal is actually getting dropped off, and instead of the metal, one oxygen molecule is coming. So here it is the oxygen, and another oxygen is here. That is here. The double bond is actually metal is removed, and the oxygen is here. And here you can see the metal is actually getting coordinated by this DMSO. by this DMS. Sorry, this is dimethyl sulfide. So this is actually a carbene ligand of Fischer carbene, a Fischer type of carbene. Whenever it is treated with the reagents, that is the CAN. So you have to remember, whenever you are seeing any kind of such reagent as the CAN, ceric ammonium nitrate, or DMSO, dimethyl sulfoxide, or pyridine inoxide, that is normal PYNO, or simply by air, that is the moisture or air or aerial oxygen. So in presence of oxidants, any carbene carbon Fischer type of carbene compound, the metal will be demethylated. Fischer carbene complexes will be demethylated in presence of these compounds. That is ceric ammonium nitrate, DMSO, pyridine inoxide, or air. Instead of that, the oxygen molecule will be here. Nothing will be happen, just the oxo transfer reactions will be happening. In this case, you can see DMSO is nothing but SMe2 double bond O. So this oxygen molecule will be going to this carbon, and the metal will be going to the DMS. That's why here you can see the DMSO's oxygen is now coming here, and the metal is actually going there, because the metal is actually having this metal is actually having low oxidation state. It is zero oxidation state. So the SMe2, that is the electron donor, will be donating the electron to the metal center just to stabilize it, and the oxygen is here. Also in this case, CAN also oxidizes this metal carbon bond, and also in this case, in case of the carbon, it will be bonded to the oxygen. So in both the cases, whenever you will see any kind of this Fischer type of carbene is treated with this kind of oxidative reagents, it will be oxidative cleavage that will be operating. So this metal carbon bond will be oxidatively cleaved, and this carbon will be bound to this oxygen. So in all the cases, demetallation will occur, and they are having this keto kind of compound. Since they are actually bound to this oxygen, in both the molecules, both are actually having this ester kind of linkages here. Pyridine inoxide is also similarly responsible, because pyridine inoxide is also capable of transferring the oxygen. It is nothing but this PYN plus O minus. DMSO is dimethyl Me2S plus O minus, and CAN is actually also capable of oxidizing the MC bond. So oxidative cleavage will be happening whenever a Fischer type of carbene will be treated with such compounds: CAN, DMSO, PYNO, or simply by keeping it in air. This is the second. This is the next reaction we will be discussing. This is the predict the product of the following reaction. When this FeCp minus molecule will be bound to this diphosphino molecule, 1,2-diphosphinoethane will be bound to this, and this carbon compound will be bound to this CH2OMe, this etheral moiety. Whenever this is treated with trifluoroacetic acid, that is TFA, at minus 50 degrees Celsius, and then it will be treated with this vinyl ethyl ether. What is the product? So in the first case, you see that is the iron Cp minus is actually there, and this bound to this CH2OCH3 ethadiol moiety, and the diphosphino group is bound to this diphosphino group is actually bound to this iron center, and the Cp minus is there, and the CH2OCH3 molecule is there. So whenever it is treated with this very strong acid, trifluoroacetic acid is a very strong organic acid which is having its pK in the range 2.3. So it is a very strong acid. So what happens in this case, all the metal center and this ligand center is actually neutral to this carbon, this bond state, or this bond state as is organic acid. But in this oxygen atom is there, which is nucleophile. So this oxygen center will be protonated by this trifluoroacetic acid. So but whenever it is protonated by this OMe group, this OMe will be this MEOH. So it will be liberated as methanol, and this this bond will be cleaved down to this Fe carbon double bond, and it will be treating as Fe double bond CH2 and plus. So it will be having as a cationic kind of group. This is actually termed as a carbene transfer reagent. Why it is so? This is actually a Fischer type of carbene compound, because you can see this iron center is actually bound to this Cp minus, which is electron donating, and this phosphorus are having high electron donation property but a very low electron withdrawing property. That's why, and this carbon are actually having no heteroatom kind of substituents. That's why this compound is having more kind of Schrock type of behavior or triplet type of behavior. So triplet type of Schrock carbene is actually able to transfer the carbene carbon to the other centers. So that's why In this case, the iron compound bond is actually very not that much strong, and it is actually classified as a carbene transfer reagent. This carbene complex is a poor source of free carbene. So whenever it is treated with this vinyl ethyl ether, this double bond is actually an electron rich thing, because it is actually bound to its oxygen, and this oxygen, because of the donation of the electron or this Brasser effect, the electron density of this olefinic double bond is actually increased. So it will be then attacking this free carbene, because carbenes are actually electrophilic in nature, because their octets are not fulfilled. They are actually 6 electron moieties. So this double bond will be treated with this carbon, and this cyclopropanation will occur, because the double bond, these two carbon atoms will be bound to this CH2 by this by and form this cyclopropyl moiety. So from this vinyl ethyl ether, they're actually having this moiety. These are cyclopropionated moiety. So here, by the aid of this protonating this CH2O CH3 group by TFA, and then liberating this methanol, and then performing this carbene transfer reagent, formation of this carbene transfer reagent, and capturing it by this vinyl ethyl ether, they are actually going to cyclopropionation reaction. So right now, so till now, we have actually discussed a lot about the Fischer carbene and the Schrock type of carbene, and also we have actually discussed about the intermediate properties carbenes, which are carbenes who are having this intermediate kind of properties between themselves. So now we are actually having some basic comparisons how they are actually classified as Fischer carbene and which are actually classified as Schrock type of carbenes. So right now, I have all the things are summarized that I have shared with you. The Fischer type of carbenes are actually having this middle to late transitional metals in low oxidation state. Here you can see, in all the cases, chromium is actually middle transition metals, not early, and they're actually having the low oxidation state, because the COs are actually neutral molecules. That's why this chromium is actually lying in the low oxidation state. And also and in this case, the Schrock type of carbenes are what? They're actually early transition metals with high oxidation state. So tantalum is actually a molybdenum tantalum. They're actually early transition metal which are behaving as a Schrock carbene. Here you can see they are actually all bounded to this negatively charged ligand. This sigma donation property of the ligand, Cp minus ClCl. So tantalum's oxidation state here, it is only +3, but the chromium here is 0. That's why the metal is in high oxidation state, and also is an early transition metal. So the middle to late transition metals are actually characteristics of Fischer carbenes, and early transition metals are actually characteristics of Schrock carbenes. The carbene, let's come to the carbon center then. I have actually stated a lot on the carbene, properties of the carbon. The carbon is actually here electron deficient, electronically deficient, because the chromium, the metal is electronically efficient, negatively charged. So the carbon will be positively charged. So the carbon is electron deficient. So if it is electron deficient, it will be attacked by the nucleophiles, that is the negatively charged molecules. So they will be stabilized by these heteroatom and the aryl groups, because the carbon is actually having this carbocationic behavior. So the molecules that are actually capable of donating the electron to the carbon and satisfy or stabilize it will be actually able to stabilize it. But in case of the Schrock carbene, the entire thing is actually reversed. In this case, the carbon is actually electronically rich, because tantalum is electronically more electronically deficient. So the carbon is actually here is electronically efficient. So the electronically efficient molecules will be attacked by the electrophiles. So the electrophiles are actually nothing but these protons or SO2 or SO3 kind of molecules, and they are actually destabilized by any kind of heteroatoms, because they are already negatively charged. So if we are actually connecting it to the OMe kind of groups or SMe or the phenyl groups, there will be lone pair electron density repulsion between these two centers. That's why in all the cases of Schrock carbene, the carbon is actually bound to either this neutral hydrogen or any kind of alkyl groups. Majority of the Fischer carbene compounds are actually obeying the 18 electron rule, but the Schrock carbene compounds do not obey this 18 electron rule, since they are actually staying in their high oxidation state, and Cp minus the tantalum is +4 in nature, and Schrock type of carbene are 2 electron donor. You can see the 6 and 2 are 8, and these two are actually 2 electron donors. That's why they're actually 8 plus 4 is 12. So it's a 12 electron system. But here you can see in this case the 5 into 2 is 10, and chromium is actually uh, 4, so it is actually having this oxidation state 14, and this 4 electron donor carbene compound is there, so it is a 18 electron complex. Here you can see that is actually, I have already stated, any kind of Fischer carbenes are singlet in nature, but the kind of Schrock carbenes are triplet in nature. And lastly, what is the most important difference between these two carbene compounds is in their MC bond strength, the metal carbon bond strength. I have not discussed about it till now. The metal carbon bond, you can see both are actually double bond, but in case of Fischer carbene, the bond is relatively weaker. So it is having a rotational barrier only in the range 10 to 15 kilojoule per mole. But in the case of Schrock carbene, the metal carbon bond is stronger with high rotational behavior, that is 60 to 100 kilojoule per mole. So the rotational barrier around this metal carbon bond is quite high. So here I can actually suggest a possible way why it is such, because you can see, because this is chromium, this is carbon, and the metals are actually meant to be electronically deficient or positively charged, and carbon is electronically efficient, it is negatively charged. But in this case the thing is reversed. In case of Fischer carbene, the metal is actually negatively charged and the carbon is as more electronically charged, or is electronically efficient. That's why the bond strength between the chromium and the carbon is not that much high. That's why the bond is quite weak. But what happens in this case, the tantalum is already positively charged and the carbon is negatively charged. That's why the bond between the metal and carbon is actually quite high here. It is actually going along with the actual metal carbon analogy. So that's why the metal carbon bond is quite strong. The bond order is quite high, and the rotational barrier is also quite high. That is 60 to 100 kilojoule per mole. That's why that this, if their two substituents are actually the same, that is hydrogen and hydrogen, two hydrogens will be coming into different region in the proton NMR spectra. But here in that case, since the metal carbon bond is, the rotational barrier is quite that much high, that's why if the two substituents are same, these two protons will be appearing on the same, because the rotational barrier is low. That's why the rotation around the metal carbon bond is low, so the NMR will be not able to distinguish between these two protons. But here, since the rotational barrier is quite high, that's why it will be distinguishable between the two protons. So there will be two separate NMR peaks in the proton NMR spectra. Coming to the last question, again we are coming to the same compound OSClNO PPH3 whole 3, when it is treated with diazomethane, and again it is reacted with SO2. What happens? In the earlier example I have already told that it's a very much well class of compound which are having properties between that of the Fischer carbene and the Schrock carbene, because they react both with the electrophiles such as sulfur dioxide or hydrogen. Hydrogen means H plus or proton, or nucleophiles such as CNR, that is RNC. RNC is nothing but this isocyanide, or CO, that is the free carbonyl. So when this OSCl NO whole 3 will be reacted with this diazomethane, what happens in this case, with the concomitant release of this neutral PPH3, this OS will be bound to this OCH2, that will be bounded to this OS double bond CH2. This is a special class of carbene which is having properties intermediate in between this Fischer carbene and Schrock type of carbene. So already in the previous example I have stated how this ClNO PPH3 whole 2 OS double bond CH2, a special type of carbene, is formed. Now the reaction between this carbene, actually noted between these two PPH3 by the crystal structure of this compound, the two PPH3 are trans to each other, one another, and this NO or Cl actually cis to one another, and OS double bond CH2 is there. Here you can see in the osmium is bound to this very strong pi acceptor NO, and the chloride are also actually capable of dragging the electron density from the metal center. Also the PPH3s are also there, but the carbon is actually not attached to any heteroatom containing substituent. That's why this carbene compound is actually having intermediate behavior or properties of Fischer and Schrock type of compound. So whenever it is treated with this sulfur dioxide moiety, that is a potential electrophile in nature, this CH2 minus will be attacking this sulfur because it is electrophilic in nature, and this oxygen, this double bond will be down taken up by this oxygen, and this O minus will be bonded to the osmium. So this cyclic reaction will be taking place, and we are having this OSOSO CH2 kind of moiety, where the CH2 is the carbene center will be bridging between this osmium and the sulfur moiety. So here also in the same compound, when it is treated with the CNR or CO, the nucleophiles, then it will be reacting with this osmium. So such kind of carbene compounds cannot be classified in the special genre of this Fischer or Schrock type of carbene. Instead, they are actually having these intermediate properties, and depending upon the reaction medium, they will behave like Schrock or the behave like Fischer kind of compounds. In case of this, since SO2 is a very strong electrophile, this osmium CH2 bond will be polarized on the carbon mode, and this C minus will be bounded to this sulfur center, and this oxygen will be bound to the osmium, producing the cyclic compound. So so now you can so going through all the questions, I have actually going through all the questions here. Now if you have any queries, you can go on and ask.